We are introducing S3Net, 3D LiDAR Sparse Semantic Segmentation Network for point cloud. Introduced by Ren Chen, Rai Razani, Yuan Ren, and Bingbing Liu. This is brought by Huawei Noyas Arc Lab, Toronto office. Point cloud semantic segmentation has become popular in recent years thanks to the quick development of autonomous driving industry. Usually, a 3D point cloud can be processed by projecting into 2D range view or voxelized into 3D grids to perform convolutions. But due to the sparse property of point cloud, doing dense 3D convolution is not practical and waste of the resources. Thus, people proposed sparse 3D convolution. For example, Minkowski engine from Stanford Vision Lab, which we built our project on. Sparse convolution was initially brought from 2D image realm, where they do sparse convolution on submanifold. Namely, the convolution output will be counted only when the kernel center covers an input side. Likewise, we can extend this idea on 3D data. Instead of introducing 3D kernels to slide through the voxel grids, we squeeze the data into a hash map and perform convolution by querying the neighborhood. The feature of current point is projected into submanifold first, and then aggregated with neighborhood. And the convolution kernel weight matrix was updated only if the corresponding neighborhood offset has elements. Based on this concept, we can build an auto-differentiable library upon those sparse data. Here, we introduce the design of a novel network and its pipeline. A 3D point cloud is first voxelized and converted into sparse tensor, a data structure that has two major components, coordinates and features. Coordinate is used to do the spatial neighborhood query and downsample upsample mapping. Feature is bind to each coordinate, which is equivalent to the feature map of an image. Each column of the feature vector represents a channel. The input sparse tensor initially have 4 feature maps, intensity, and 3 channels of novel vectors. The sparse tensor is first fed into the sparse convolution with kernel size 5 to project the neighborhood features into 64 channels. Then followed by a sparse average pooling layer with kernel size 3 and stride 2 to downsample the data. The downsampled sparse tensor is then fed into 3 consecutive encoding blocks. Each encoding block contains 1 layer of sparse conv, 1 layer of sparse intra-channel attention module, 1 layer of sparse inter-channel attention module, and a sparse residual tower layer. All those layers will be further introduced in the following slides. Similarly, the decoder blocks consist of sparse transpose conv, sparse interchannel attention module, and sparse residual tower. Sparse tensors maintain the coordinate mapping. Thus, the neighborhood information can be propagated accordingly. When the sparse tensor stride recovers back to 1, which is the original resolution of the voxel data, we perform another point-wise convolution to produce the semantic probabilities for each point. Now we are going to introduce the modules mentioned above one by one. Let's start with the sparse intra-channel attention module. Sparse intra-channel attention module extracts the sparse tensor feature in a very large receptive field. Then, a point-wise feature channel compression layer compresses each point's feature vector column-wisely, also known as channel-wisely. Then, they are decompressed by a following point-wise sparse convolution that projects the feature compressed submanifold back to the original shape. The compression and decompression of the original feature map after a large receptive field is serving as a query key, whereas the key is later on multiplied with the input value tensor. This hierarchical attention mechanism is also known as transformer in neural language processing domain. Sparse interchannel attention module is more like a squeeze excitation on the sparse tensor, where all the point features are aggregated into one row of feature vector by a sparse global pooling layer. Here, we use the sparse global average pooling. The aggregated feature vector is compressed and decompressed by a fully connected MLP, and then the single row of the feature vector is filtered with a pointwise convolution afterward. Each column of the 1 by n, which is 64 here, feature vector is multiplied back to the input sparse tensor's feature map to emphasize the sparse tensor's feature map column-wisely for each point. We observed gradient vanishing after introducing this submodule, and sometimes result in divergence. So to eliminate this artifact, we introduce the damping factor lambda, which takes the original data as a basis, and then 1 minus lambda as an offset. The scaling effect of squeeze excitation can only affect the offset, and we can adjust the contribution of the submodule by adjusting lambda's value. In our experiments, lambda is empirically set to 0.5. Sparse residual towers consist of two branches. The top branch is a sparse convolution with stride of 2, followed by two pointwise convolutions, whereas the bottom sparse convolution has the same kernel size but do not perform downsample, which is the stride is 1. Its output is used as a residue to recover the input sparse tensor's coordinate map and their corresponding features. By doing so, the higher layers of the features are condensed into downsampled subsets, whereas the pointwise features at the original resolution are still kept and flowed into the upcoming blocks. Since the flow is like a tower shape between each block, we name it as a residual tower. Our customized loss function has two major components. One is the weighted cross entropy. Two is the local GeoAware loss. We define a local GeoAware term by calculating the neighborhood anisotropy of current point and pointwisely scale the entropy of each point. The anisotropy is defined as 1 if the class label is not equal and 0 otherwise. When the network has a higher confidence on the semantic predictions, the major area contributing the error lies on the boundaries of the semantic classes. This local GeoAware term has large value around the borders and diminishing the effect of the center for each semantic areas, which is geometrically equivalent to the focal loss. Following is our experimental results. As we can see from the table, our method is the state of the art upon the publication. Up until now, it's still ranking 6 among hundreds of submitted methods. Additionally, we list our ablation study table here. From the table, we can see that the biggest jump of the real classes came after the sparse residual towers. This is a demo clip recording our algorithm running real time.